Awesome. Thank you. You good, Alpesh?
Yeah, started.
Great. Okay. Hello, everyone, and welcome to the seventh OTC Talks session. Um, just before we get started with the talk, I'm just going to talk a little bit about OTC in general. If you're new to our community, so OTC is our tech community. It's an open to all tech community. We conduct a lot of sessions. Two of the most prominent ones are OTC Catch Up and OTC Talks. OTC Catch Up is an online informal discussion that happens every Saturday night, 10:30 p.m. IST. In fact, today is the 250th session. We've been meeting consecutively for the last 250 Saturdays now. So please feel free to join us. These are informal tech discussions. We just discuss things about tech. You can bring your project. You can talk about anything that you wish to regarding tech. So come join us. Today's the 250th session. Right after this talk, we will start our catch-up session. And so this was OTC catch-up. The next thing that we do is OTC talks. So OTC talks, today is the seventh talk that we're conducting. Essentially, the point of OTC talks is to get in-depth technical knowledge so we can learn from people who are very experienced, right? If you want to give a talk, there is a CFP that you can fill in. Darshan will paste a link in the chat. Yeah, so that brings me to today's talk, where we have Vivek, who's going to be talking about browsers. Just a little bit about Vivek, although he will give a more elaborate introduction. Vivek has 20 and more years of building browsers, and he's contributed to projects like Chromium WebKit, and he's also the founding engineer of the browser company, which is the company that started with Arc and now Dia, right? So extremely excited to have him here tell us about browsers and how he fixes issues, how he diagnoses issues with browsers, and we might also talk a little bit about some security stuff. So Vivek, over to you. Thank you so much for joining. We appreciate you going to your office at this time in the night and conducting the session from there. So thank you so much. Appreciate you.
Hey, thanks, Harsh, and everyone for the opportunity. Because I think one thing is I'm really passionate to share the knowledge. And also given that I had a multi-monitor setup at the office, it made sense to come to office. So it's a blessing in disguise both ways. So thanks for that. So hey everyone, welcome to the talk today. So today I'll be talking about the peak in performance. What really goes inside your browser. So basically, I conduct these talks under the name that the browser backstage, where you would get the insights of what really goes inside your browser that you use for various purposes. You might be a developer, you might be a casual user, you would just be using browser in any capacity. So it doesn't really matter which stream you belong to. So today's talk is going to specifically focus on like how, as a browser engineer, we work on performance, because typically there's a set notion that, okay, hey, whenever you don't get your browser to do certain things, you would blame that a browser is not doing good. It is actually probably we should see a little bit more than what is it the browser which is taking more resources, or is it the website which is actually causing the delay overall. So this talk is going to demystify a lot of those like notions. So I'm just going to use in the same presentation so that I don't have to go to this one. So let me know if you can see this in a proper way. I can remove the
Yes, this looks good.
Okay.
Yep.
Okay. All right. So hi everyone again. Myself Vivek. I have been working on browsers, building browsers more than 21 years now. In fact, this presentation was 2 years old, but currently building Dia and Arc at the browser company, as Harsh already mentioned. So I'm a reviewer and a committer on the Chromium project. So if you have ever used the dev tools in your browser, so I have contributed heavily in that area, and as well as I am the owner for doing the JavaScript to C++ bindings that you would be using. So all the JavaScript APIs that you use, how they are actually interconnected with the underlying C++ is what I contributed and became an owner over there. So that's my work on the Chromium. I started my open source journey way back in 2006-7 when I was at Nokia, and I used to contribute to libc. I mean, we had a libc version for Symbian. If you anyone of you know Symbian what it is, so I contributed to that one. And then formally, I started contributing to the browsers because we were also working on the browser runtime back then in Nokia. So in 2009 or 10, I started working or contributing to WebKit. So the very first commit that I did on WebKit was indeed for the inspector work. I mean, you might be using Safari or you might be using like Chrome. So it all started in WebKit. It was called Inspector back then. It is still called Inspector in Safari or WebKit, but that's where the first commit came in. And then I have worked across different domains like mobile, automotive, IoT, and to some of the like not handheld devices, but the virtual reality devices. So I worked to build a browser in Samsung for I don't know, it's no longer there, but it was one of the device that you can wear, whatever is HoloLens or Apple Vision Pro. So very first incarnations of that one. So previously, I have worked at different companies, and then predominantly, I have worked into the system side, compilers as well as into the browser side. So that's a brief about me. I'm very much active on X if you happen to be there. So I'll be happy to connect over there. So let us start with a slow browser demo itself because it's a browser talk, and without a demo, it's not going to start. So can you see this? I will come back to this guy. Okay.
Yes, we can see it.
Okay. So think about it like this is a very much contrary example of a typical interaction that you would have on any web page where you would provide your text input, something like this, and it works perfectly fine. I mean, there is no issue with that one. But think about it like if you have an interactions like a Grammarly integration or some of the other integrations, and then it would start uh, a lot of the interactions that would happen with the servers here. So for example, let's say now that I have added a virtual relay, this is, as I said, this is a contrary example just to showcase the problems that we would face. And this might not be the exact real world scenario, but this would give you enough insight so that you can start looking at the right probes when it happens. So I have started typing here. This is amazing. I have typed. I really don't know what I have typed because it's not appearing on the screen, but this is exactly the demo here. And eventually it would come. Yeah, and see there. I mean, I typed and then it is kind of all garbled here. So this is the demo with which we would start, and then the whole talk would be around like how do we get around these ones. Okay. So this was a little bit of a video that I had in case this did not work. So I'll directly go to the browser architecture slide here. So this browser architecture is now universal across all the browsers that you use. Let it be Safari, let it be Firefox, Chromium, obviously. So you will have a multi-process architecture, and yeah, so this is the very high-level architecture. So you would have the user interface layer, which is nothing but how you would see and interact with your browser, and it actually has a main thing which is called as a browser engine, which is I have kind of used the different names here, not to be very much biased with what Chromium uses, so that you can actually extrapolate that to any other browser of your choice. So browser engine, or basically the main browser process, is the one which is actually driving the whole show. So all your interactions like inputs, including your keyboard, including your mouse, or like any other external devices, all those will be connected and have access to your disk storage, file storage, everything will be managed inside the browser engine. It is basically the super uh, privileged process over here. And then its primary responsibility is to like orchestrate all your web pages along with features like autofill, location, history, all of the like usual suspects inside the browser, spell checker, everything. And these days, a lot of the AI stuff actually is also integrated into that one, so that you can see. Uh, but the main interesting part here is the rendering engine or the rendering process. Again, I have used the word engine here, not to be again biased with the processes, threads, and all those things, just to keep it high level. But then the rendering engine or the rendering process is responsible for parsing layout, paint, and various phases of your page. Don't worry about all of these ones. I have few details that I have covered. Obviously, this is very involved topics. For each one of these box can actually go into like a various depths of all the concepts that we have studied in the computer science. So including compilers, including garbage collections. A lot of these things actually happen, but today's scope is just to kind of look at the performance part of it. And as I was saying, like there's a JavaScript engine, which is responsible for your interaction and having interpreted as well as the just-in-time compilation modes. And it has all these phases like parse, bytecode, interpreter, and JIT here. Networking is actually handled out of the process. So your web page will not have a direct access to the networking stack, and it is actually handled out of the process. So even if you are trying to load like any web page like google.com on your in your tab inside your browser, so it will not be actually directly accessing any of the network thing in there. So it would be actually separated and it would be running inside a utility process. So all of these details actually you can see it right now. I can show you if you go to like your browser, Chromium-based browser, so you can actually see that here. So there's a task manager, which would look like this. Unfortunately, I can't zoom uh, the font over here. This is going to be, you'll have to make do with it. But let me see if I can do something with that. Yeah, can you see it now here?
Oh, yes, that's clear. Thank you.
Okay, so here is where you can see that this is the main process browser. And then here you have a GPU process. I'll talk about it, but this is the network service that I was talking about. So it has a separate network process, and then there is storage. There are like various different things. Right now we are doing a video call. So there is a video capture service that is going on here. I have started a lot of the other processes. So you can see all of those things in here. So you can see all of this in your Chrome browser as well. Let me just run Chrome and just show that so that it's visible. Yeah, can you see this? Okay, so once you're in here, you can actually go to the more tools, and then here you will see task manager. So this is like a 3 dots, go to the more tools, and then you can actually open a task manager, which will exactly have the same thing. And this is barebone that is running now because no tabs are there. So let me just show you here. Again, I can zoom in here, but let me load something. So you can see that I have loaded a page, and then you can see that those are all here, and then like a lot of these things would happen. I mean, again, I'm setting the context here. Don't worry that if you don't understand all of it, that's the role here to show that. All right. So now that we have seen like what is the browser architecture. So there are a few things which are actually handled uh, out of the device or basically on the cloud. So basically these are your updates, analytics, and sync. So you would want your like locations, history, all of those things will be synced, or also the extensions that you are installed. So all of that thing actually is handled by a service on the cloud. This is an opt-in service. So if you don't, basically you can have this one. So moving on to the next one. So this is the multi-process model that I just showed you, like how this actually works. So again, this is a very simplified diagram that I have created so that it is digestible and not very overwhelming. So you start with the UI process or the main process. That's where when you fire up your any browser, it would start with this, and then as and when you are creating a new tab, basically a new render process is actually created. So WebKit calls it as a web process. So I have used both the names here. So Firefox, I think they have a very something similar. I think they call render process itself. Now, the roles and responsibilities are clearly outlined in this one. So there is a shared memory as well as like using the IPC mechanisms. All these processes would communicate with each other. And you might ask, why is that we need to kind of create something like as complex as this multi-process model? So remember, I mean, some of you might remember that when one of the tab used to be non-responsive, you had to kind of close your browser and then like relaunch whole of the browser again. And that's where Chrome came up with this multi-process model. That was the first browser which actually had come up with this one, so that your I mean, I always say that your browser is the commodity product. When I say commodity product, you don't really think about how you use your browser. You want it to work uh, like a rock solid. I mean, you really don't want it to be giving you trouble, right? So basically, to make that experience like seamless, so this multi-process model was outlined in the way back in 2008 in Chrome first. And after that, it was picked up by almost every other browser engine there. So the render process is the one because that's where we have all interacted with when you like load any web page. It will have HTML, CSS, and JavaScript. All of those things will be actually handled inside the render process. Their parsing, their semantics of how the CSS layouts are applied to the HTML, and then how these are actually translated into various trees. I have shared a lot on Twitter about these ones, but if you are interested, you can actually look at that and I'll be happy to answer any of those questions. But then the way that these processes communicate with each other is via the IPC, and Chrome uses something called as a Mojo, which is an IPC framework that they have built it, and they internally use the, the core native OS primitives because one of those, I mean, those are the ones which are actually the fastest mode of communication between the processes, and also having the security in place. Uh, Also, when now a lot of the web APIs that you use have evolved over the years. So the very fact that all of us are trying to have this, not trying, or are having this meet inside your browser is the success of the web technology that you're seeing. A lot of the like complexities of which video codecs to actually use, which web codecs, or like how the synchronization happens, how the signaling happens. All of it is actually hidden inside these complex parts inside the browser. But then, as the capabilities started getting added to the web, it also required to have a security in place. So imagine that we also have a file writer APIs. File reader was there, but file writer is also there. So you can have your one of the web page creating a file or editing the files, and definitely you don't want that to happen on your machine uh, without security in place. So this is where a sandboxing thing comes into the picture. So I am going to go in a different slide. Yeah, I hope this is visible. So
Yes.
so all of your web process, which is actually running, it requires a lot of the permissions. For example, your microphone, your camera, your location, network files, input, even input, your keyboard, everything, and the storage as well. Okay, so DOM storage as in like IndexedDB and all those databases that you might be using. So all of it requires a permission, and because, as I mentioned, this lives and only the super privileged system of the process in your system is the browser process. So it has to broker through this UI main process over here. Everything has to be kind of vetted by this particular process. And if there is a missing permission, a user prompt would be thrown at it. So of course, the browsers have been at bad implementations of some of these permissions. You might be getting a nagging permissions like, okay, would you like to allow this notification? Would you like to do this? So all of those things are actually handled by this guy. So you know where it is coming from. And as I mentioned, so this runs in a completely sandbox environment. You will not, this process per se doesn't have any of the access to any of these things directly. So it has to go through this. And this is where the IPC comes into the picture. So this, I have again mentioned here shared memory, but this is an IPC block over here. And I'm going to talk about this GPU process a little bit right now because this is an important thing. So all of your UI that you see is all hardware accelerated. So a lot of the composition, a lot of the not only the the UI parts, but also the video decoding also happens on a GPU process. So if you are depending on which video codecs are used, if they are accelerated, they are all actually handled outside of this one. So think about it like if you are loading a page, a website like a Pinterest, it has a lot of these images that it shows up, right? So all of these are for the render process. These are all the textures, and these are all the textures uploaded to the GPU process for doing the final compositing over there. So, and then this GPU process is not only responsible for that, but it is also responsible for getting your video frames out, I mean, decoding that. A lot of the hardware accelerated decoders are also accessible via the GPU process. So GPU process is not only working on the GPU alone, it's a graphics process. So it has access to like all the things that we talked about. But again, it is also sandboxed in a way that it doesn't have access to other subsystems, which it need not. So it has access to your GPU drivers and all, but it will not still have access to your file system because uh, the the point of contamination has been kind of limited for safety, more of the safety and security reasons. So yeah, I'll pause a little bit here because I don't want to be this just a monotonous talk. So if there are any questions on these ones, I'll be happy to take like midway as well, so that the context is set and then I can answer them later.
Yeah, everyone can, whoever wants to ask a question, you can either put it in chat or a better way would be to just raise your hand and you can ask your question directly to Vivek by unmuting. That would be the best. Yeah, Darshan, go for it.
Yeah, I will go first. So, by this diagram and all the previous diagrams that you've done, so correct me if I'm wrong here. So, all the processes communicate through the main process or the UI process, right?
Yes, I think I'll give this
So,
on the yeah.
yeah. So, essentially, each tab has its own UI process, or it is a centralized browser level process.
Yeah,
That was my main question.
correct. The UI process is only one. That's your whenever you will fire a browser. So that's the process. So I'll just go to this one. Just that. Yeah. So here is where you can see that you will see a browser here.
Okay, that
So
is the UI process.
that is the UI process, and that is the super privileged process, which has all the access to everything. And this acts as a broker with the rest of the system. So your
Okay,
web
so
pages, they live
only
here.
the renderer are the
Yes.
other tabs,
Yes.
and rest of the things are just single processes.
Correct. So you can see here that these are all my tabs which are running here.
So if we have multiple tabs making network requests at the same time, so uh, is there a chance we can overload the network process itself, right?
Yes, absolutely. So
Okay,
basically, there
okay,
is a rate limiter that is applied on like how many simultaneous network requests each renderer can do it. So it ranges between 2 to 4, just to kind of have a fair policy between the rest of the renderers. And the network process is responsible for doing the network connections here. So this is actually it lives inside this utility process here. So this is going to be
My,
like,
yeah, go
go
ahead,
ahead.
sorry.
No, this utility process is kind of an array of process. So if I can go back to this is getting stored. Yeah. So here you can see that these are all utility processes over here. So extensions, whenever you install extension, they are all actually part of these ones. So uh, there's some interesting thing that I'm just going to share here. So you see the spare renderer. So if you guys have used fork system calls, so this is where your fork is actually created. So you have a spare renderer, which is like a initialized system that is kept. And every time you create a new tab, it's actually forked from this one. So it has the bare minimum system resources that are keeping here. So I mean, I just shared this bit so that
So
you can
just to
correlate
make
that.
the
Yeah, yeah.
opening tab experience better.
Yes, and have it
Yeah.
much faster. So you can see that its size is right now. It did not capture when I captured the screenshot, but I can always see what's the current memory footprint it has got. So it has got uh, 20 MB. Okay, but whereas
Mhm.
my Google Meet is running at what 128 MB, but you see my GPU process because it's kind of consistently doing it. It's 4 GB. So this is where the magic starts, and
Yeah.
and you can
Uh,
see that the CPU
I
is
had another
constantly.
follow-up question as well.
Go ahead.
So again, might not be important for this talk, but the thing which I wanted to know how it prioritizes tasks. So let's say we are on a Google Meet and you are making some other requests in multiple tabs and like basically having multiple connections open. So how does it prioritizes that?
Right. I think that's a really good question. So if you recall from the classical definitions of scheduling, so we have FCFS, we have fairly like a fairly I don't know the name, but then so those are the various classical
CFS.
CFS. Yeah, correct. So those are the various scheduling algorithms. But what we do here is also we take into account which tabs are visible. Okay. So there are a lot of the optimizations that are done that I would like to share. So for example, when you open a YouTube and then you have basically switched the tab, so the video decoder stops basically because it doesn't have to generate those frames and it doesn't have to basically composite that anything unless you're into a picture-in-picture mode. But then coming back to it, we also do a lot more optimizations where your JavaScript is throttled for the non-visible tabs so that they don't take up too much of the resources. So it is likely that some rogue web page can just start and run inside the background and then try to do a DDoS kind of attack. It's not really a DDoS, but denial of service on your local machine where your browser is unusable. So all of these things are actually handled inside the scheduler. So there are like various different types of schedulers that run. I mean, for each different function here. So in a nutshell, yes, there is a scheduler which actually does mix of all of these ones that I talked about from the scheduling perspective.
Pranav?
That's a
And
great question.
that is managed by the main process as well.
Yes,
Right?
yes,
The information about the tabs and activity.
yes, yes.
Okay. Yeah, that was it. Thank you.
Thanks, Darshan.
Yeah, I'll just try to keep it short. So the way I see it, this like the utility process is going to be the main parent process, which is going to handle all the other child processes. I just wanted to understand how is the IPC mechanism being handled between different tabs, because there might be some Chrome extensions or some tabs that are going to talk through. Are those browsers going to use something like a semaphore for producer consumer problems, or are you just going to like have a like an unnamed pipe sort of a situation where you just keep pushing your content to one side and then the other process just pulls it out and just uses it? Or is there some sort of communication going on through these files as well, and is there a locking mechanism maintained internally?
Maybe it's a too like a big question, so it's fine if you keep it short. Yeah.
Yeah, I'll keep it short because each one of these questions is really a talk on its own, because I love to actually go through them, but then due to the timing restrictions, we would probably restrict it to this one. But the two tabs cannot talk to each other even through the IPC, because you would have to kind of limit that and also see the security vulnerability. That imagine that you have opened your Gmail and then another extension having like rogue extension, obviously, and then through which your like rogue.com page is trying to have access to your Gmail. So
Hmm.
basically, that will not be directly talking to each other. Those tabs will not be talking to each other. Everything will be brokered via the UI process here. Okay.
Got it.
So it uses like a lot of the synchronization primitives that you mentioned,
Hmm.
semaphores. I will have to dig into the details, but definitely I have seen all of those things
Got it.
in the code base. So definitely it runs through that one.
Got
So
it.
yeah.
Thanks.
All right. So if there are no questions further, I can move to the next one.
Yeah, I think we can move on for now.
Okay. All right. So this is the rendering pipeline. This is one of my favorite slides here. Okay. I think there is one more question. Ayush mentioned something. I saw that. Do you want to? Where is?
So I was just
Okay.
thinking that we can like take them later on, right?
Okay. Sure.
That kind of
All
thing.
right.
So feel free to stop whenever you want to for questions, but the longer ones and stuff we can punt them to later on.
Sure. All right. So this is the rendering pipeline, and this is my own visualization in terms of how I see this. So think about this is your web page that you're trying to load, and the example that I have taken here is your YouTube, like how it progresses over time. And this is like a train track that you see here. And then between each segment of I don't know what to call these ones, but you have these time that you get it, which is like for the 60 FPS, you would get a 16 milliseconds, 16.66 to be precise. And then between these frames, you have to actually do a lot of work that actually goes on. Okay, so before we kind of look at this, just try to see from the user's perspective, and then we will get into this side. Okay, so when you are trying to load your any web page, and here the example is YouTube, so you would see something like this. It would start with some placeholders, and then as the time progresses, it would probably has started showing you thumbnail of certain videos. Certain videos are still kind of like thumbnails are still getting loaded. Your text or the comments section below is also getting loaded. And if you happen to see, YouTube actually optimizes and comment section loads at the last. Okay, so that the first display is like the prominent display of what you are trying to look at it. So those are all actually handled here, and they are not in this case, but you can see how this is actually progressing. And at the last, you can see here this like a colored thing, which is like your page is ready for consumption. Okay, so this is the way that the visual progression happens. And now within each one of these ones, what is really happening? So for the first time, you would see that it is just kind of bootstrapping and doesn't happen much, because this is where the most of the heavy tasks are actually happening. For example, fetch. You will have to download what page or the HTML content that you have to share, along with the bunch of other things like JavaScript and CSS. So it's actually part of the fetch. Not only that, it has to do parse, execute, and garbage collection for your JavaScript. And also it has to do the layout, styles, input, paint, all of that stuff it has to do. So in the first few steps here, you can see that your frame is generated. And how many of you know vsync? I know I cannot do like show of hands here, but vsync is a way in which your hardware machinery gives you a tick saying like, okay, hey, I'm running at 60 FPS, so you have to generate a frame at this level if you want me to display it. If not, basically, it would just use the previous available frame with it and just show it up. So this is a hardware level timer that we get at vsync, and basically gets all of those synchronization things from your hardware, so that your apps which are running, they can generate the frames, and the system level compositor can show you that one. So now in this case, as the website is loading, you can see that there are two blocks which I have not shown much, but then there is a frame which is not also generated at this in between these ones. That is because the frame your renderer is busy doing the rest of the things, and it cannot produce a new frame between this. So because of that, browser just picks whatever is available with it and just shows that up. Okay. And as the progression happens, so your web page is kind of getting a lot of the details, and then it is generating new frames. As you can see that there are like a lot of frames which are missed here. Okay, so ideally, the best case scenario, you should have a frame at each segment here, but that's an ideal case. So, right. So with this, now what we have is like, if everything is so sorted, so why are we all here? I mean, what is that we are talking about? So far, I have not really started anything that talked about performance here. So for these reasons. So one of the thing is like page loading, browser freezing, or not responding, crashes too often. So these are the kind of typical symptoms that you would see. High memory usage, high CPU usage, video playback issues. Chromium is notorious for having the bad name that, okay, Chrome browser is a memory hog, but it's a memory hog for a choice, or by choice, not for choice. It's by choice because it has kind of prioritized the safety and security, and because of which you would see the one that I talked about, sandbox and all the multi-process model. It requires resources. These are not free-loading entities inside your system. They require certain resources. The goal is to keep them at the bay, I mean at the minimal. So you saw that the spare renderer, which was running at 20 MB, that's the cost that you provide, because you want everything to be fast. You want a new tab when it's open, as soon as it should be ready for consumption. So those kind of things are actually handled here. Slow startup time, missing web platform features that I want to run Google Meet. I want to share everything. That's the requirement, but Safari cannot do all of that. I mean, now it probably does, but Safari is the one which doesn't provide you a lot of the features from the web for various reasons. Yeah, and then missing shoes in my package. So this is something. So for all of these ones, so how do we as a browser engineers work with it? So before I go here, I will just like to show you in the same demo that we did, how this actually works for mm, like web developers, okay, not for the browser engineer, because let us start from that perspective and then get inside this one. So all of you can actually go to this one, and whenever the time permits, you can actually go ahead and take a look at that. And you can actually go to the performance panel here. Let me just zoom in a little bit, okay? And you can actually start recording performance trace. And then I have started typing hello, and world, I'm going to type it with a delay here. Okay, this is a synthetic delay. I have typed it. You have to believe me. Yeah. And as soon as I stop here, you can see how much the delay was there. Just going to pop this out in a separate window so that we can see the full thing here. Okay. So this is all showing you what is really happening inside your renderer here. Okay. So Uh, again, just like what we saw as the process model, even inside the render process, so you have a different thread model, okay, multi-thread model. In that you have a main thread, you have various other things which are going on here. There is a thread pool. If you're coming from a core systems background, you will have all of these ones. So this particular view is restricting you to only the entities which are needed for a web developers to understand it. So it gives you probably, let's say, 10,000 feet perspective of what is really going on in here. And the one that I'm going to show you is for the browser engineers who are actually building the browsers, where you can actually go to a minutest interaction that is happening inside your system. Okay, so to start here, right? So you can see that my interactions are going on really well here, but like those 5 characters, I specifically typed the word WORLD here. So you can literally see that this is taking significant amount of time. So each like longer block over here is representing the time that it has taken. So if I just hover on it, I have a synthetic delay of 1 second just to show the impact of these ones. Okay, so now when you are going inside this, so this has like a gaming keyboards like WASD, so you can actually zoom in to like these ones. So, and there's something interesting, and I really love to show off that one is that you will see that the frame that I showed you here, right? Like this. So literally you can see what frame was actually presented to the browser for compositing. So you can see that here. So you see that I have typed hello. It was like instantaneous, looked to us very instantaneous, but here you can see that how it is represented. Okay, so and then if I zoom in a little bit here, so if I just zoom this frames section, so here is where you will see how much time it is taking for generating that frame. It happens a lot faster, but then it is just showing you, yeah. So in this now, again, I want to know where exactly the time is being spent because you're interested in knowing what are the time like time taken. So you can actually go down and take a look at the call tree. So this is my event key press. So this is where exactly is happening. So this is my function that I did. This is my function. So I think I need to be on a right frame. Yeah, I had to zoom out because I can't see. I will just zoom back in. Yeah, so I can go back to this function here. Okay, so uh, this is my function call. You can see where is the time spent. It's like it is telling me it has taken 991 milliseconds, which is the responsible function. So if you click on this one, it takes you where exactly it is. So you can see that I have added a delay of 1 second, and then I run a while loop here. Uh, So it is taking me there, and that is the reason it is stalling, and it's not generating any of the frames here. So if I just go back, again, I will have to zoom out. But right now I'm just showing you the frames which are generated here. As long as you are able to see that, I think it's good. So you can see that during the entire course of that 1 second, there are no new frames which are generated here. And the next frame is generated only when that we are coming out of yeah, you can see that WOR has come up so far because I have typed 3 characters and waited for 3 seconds here. All right, so we spent a little time here, but let us try to understand this now. What is really happening inside the main process? So to do that, I'm going to replay this, but this time with a tool that we use that you can also use it on your machine. And I would encourage you all to try that because it's an interesting way of knowing things. So there's a perfecto.ui. So this is an extension. I'm just going to link that here in the chat if you are interested. So you got to install this. It requires you to give the debugger permission because it requires that. And with that, what we are going to do is, this is my typing delay, and I'm going to record a trace for this. So after this, you have to go to the ui.perfecto.dev, which would look like something like this, which is very similar to this one. To share. And once I record a trace, so you can see, basically it still calls Chrome because it uses a Chrome protocol to do this. And if you select the Chrome, these are the various probes that you can do, and for which category you are interested. So let us say that you're interested in the input events flow. So you can actually select that. And once that is selected, you can start the tracing. Okay, now that the tracer has started, I can go to this guy here I can type hello, add the delay word. I've typed it. Let it appear. And then I go back to this guy and okay, it stopped. Okay, because I had a timer based system. So this is my render process here that you saw. Okay, and this is my browser process. And as I said, there are like various different things that are going on. Like this is the main browser thread. There is IO thread. There is a thread pool service. So these are all threads, by the way, and how they interact with each other. There are also a lot of the bookkeeping and analytics that runs in. When I say analytics in terms of uh, when I have generated these, I would say, when the renderer is running, how many times it has missed the frame. So it has all those recorders in place. Okay, so let me just go to this guy directly so that you can see the same delay that we saw there, but here in this case. So this is where the handle input event. Okay, I can't use this one with the zoomed in because it has the restrictions, but yeah, you can see that this is my time, like input event. And what is interesting here is if I click on these arrows, so you can see that you can actually trace back, okay, from where it came, how many thread hops it has taken from. So all your inputs are actually handled, as I was saying. It is all handled inside your main process. So I mean, obviously the trace is a little longer here. So if I just zoom this thing, and again, you can use the WASD. And these are all the messages here. Yeah, so here, this is what I wanted to show you. Okay, how the messages flow between the processes here. Okay, so this is your browser process. It is sending, I mean, it has now received a message from this guy. So it is actually telling me that, telling the browser process that, okay, the frame is ready. So this is an event that it receives it from the render. So you can actually trace back the whole thing here. And then it is coming also from the network service. Sorry, this is coming from the GPU process here. So this is very much involved task. I really don't want to spend too much time here because I love going through these ones, but again, not in the current scope. So this is how the whole pipeline actually shows up, and then you could see the details in like various tracers. One that you can see for which is tailored inside the dev tools for the web developers perspective, and one is for the browser engineers perspective. So I think we were here. Yeah, so now this is where the tool that I showed you, Perfect2, is coming into the picture. It is a system profiling, it has app tracing, it has a trace viewer that we saw, and it provides a trace analysis. This trace analysis you can actually do offline as well. So you have a Python interface to it. So there are very few interesting things that I'm going to show you, not directly, but here I'm going to show you. So this is just to give you how to start looking at where is the pain point, right? I mean, because you saw that it was like very overwhelming. So this is my cue here that, okay, there is something going on wrong here. So I started exploring that here and I got, hey, this is my V8 function call, okay? And how is this related? So you can see here, this is my input latency here. So you can see that whenever you are pressing the keyword, I mean keyboard, it is actually received in this, and then it is relayed here. Then this basically handle input event happens, and then all of that stuff is taken care. And so these are my places where you see my metric that dropped frames. It is not generating the frames. Okay, so it has like these many frames are missed here. So browser was expecting, but you did not produce it, so it is flagging me that. So as a browser engineer, when we receive a request, I mean, a report that, okay, your browser is slow. So we identify who is causing the delay. So if you see these kind of skyscrapers inside the browser, so that means we are doing like the broker process is too busy. It is kind of stalling because as uh, it is a single point of contact as well as a single point of failure. our aim is to not see any of these things here. The moment we see it, we know that this is a problem. When we see something like this, we know that there is a problem, but this problem is related to the website that has been built. And as you saw, I have added that 1 second delay with a while loop, so nobody can help it. So unless you find that developer and then basically find them and then get it sorted. So this one is one of my favorite. It's like visually it looks all appealing, but what is that you can do with it? So you can literally run a SQL query on it. So here I have run a SQL query just to get me all the task IDs here, which are handle input event, because I'm interested in knowing what is the latency in handling the input events. So I have given all of that. It's not, yeah, here is my query actually. I'll probably share if somebody is interested. But once I get this, so I have actually, you can copy these results into a like a CSV or a TSV, and then you can actually do any visualization. So here I just plotted this on a Excel sheet or a spreadsheet, and then here is where you can see that these are my 5 words that I typed. I mean 5 letters that I typed. So you can see how much time they are taking and where are the rest of the events. When you don't see it, any of the lines, that means there are no events which are taking significant time, which is bothering the performance here. Okay. So now you might wonder what is in it for me. I mean, like you are a browser engineer, you kind of get to do this every day, and like how is this beneficial to like me who is not even related to browsers? So that you might have this question. So one thing is Perfecto. Perfecto is a standalone C++ library that can be integrated in languages with the CFFI, almost every language that is out there. So you can actually integrate this in your apps to see what is really going on. It's very powerful utility. It has a lot more things in it, and but you still might wonder, like, what about the overhead of tracing? You are still thinking that okay, this is looking all like nice and fancy, but what is the overhead of tracing? So this is the performance. These are the performance details which are shared. So these are the three events, like whatever you saw on all those charts. So these are all kind of events that you have to log it in your code or the functions, and how much the cost that you are paying for each one of these ones here. Okay, so they are like in terms of nanoseconds, not even in a millisecond. So this is pretty good in terms of what you can do with that. And with it, I think I'm done on the performance part of it. Obviously, I just scratched the surface just to show you around. It has like lot many insights that I wanted to share, but I couldn't due to the like time slot and the scope for this one. So till now, do you have any questions? And I don't know whether I have time to go through the security thing, which is of the interest here, but yeah, I want to know.
Vivek, you can take your time. So if there's more that you can share and you want to share, and you for whatever the scope that you have decided for this talk, please feel free. Right? We're not like, oh, it's time is done, we are ending it now, right? Like it's okay.
All right. So I'll just briefly go through these ones because these were some of the
Sure.
interesting
Take your time.
historic events that actually happened, and then these were impacting your browsers.
Mhm.
And since this is a little systems area and of my interest, I'm going to a little spend time on certain things here. So you have the CPU pipelining. How many? I don't know how many of you know, but then your processors have very sophisticated designs and architecture, not like the ones that we studied in microprocessor 8085, 8086 in our colleges. Those had like a single, not really a pipeline, but you send some instructions to it and it will execute and then come back with that. So just yesterday, I shared a very interesting website called Wikichips. If you're interested, it is there on my Twitter. So it gives you a fair bit of the complexity that is involved inside the processor design, and the processor architectures have been using CPU pipeline for almost 2 or 3 decades now. It's there in some or the other form. So typical stages of your execution for any instruction is like fetch from the memory, not main memory. It's a fetch from the memory. Try to interpret it with what is the meaning of that instruction via decode phase. Then there is an execute, which is actually executing what is required. Again, then there is a result back. Okay, yeah, this is the output or the result of the operation, and then you write it back. So these are the kind of 5 stages. And without the pipeline, you can see that and the clock cycles, right? I mean, you know that my processor is at 4 gigahertz. So what is the speed? So basically 4 billion operations that you can do in 1 second. So in each one of these like slice of 4 billion is basically a cycle. And in that cycle, what's really going on here? Okay. So without the pipeline, so the one that we studied in the textbooks, when I say I studied 25 or 27 years back, but it might have changed a little bit. But this is your instruction 1 that is coming in. Then currently it starts with the fetch, then goes to the decode, execute, memory, and write back. And until then, you can see that like if it is taking 6 cycles, again, this is hypothetical just to represent that. We have the next instruction coming at cycle 6. But with the pipelining, what really happens is when your CPU has completed one instruction and going for the decode, it can actually allow for the next instruction for the fetch phase. So this is a very simplified view, again, just to kind of keep it very easy. So then once these things are in place, so there are some more interesting pieces that browser actually, I mean, not browser, basically processes they employ. One of them is the branch prediction and the speculative execution. So again, in a very layman's terms, so let's say you have a condition block in your code. It could be any code. It could be your C++. It could be your assembly. So because at the end of the day, there is a conditional jumps that processor has to take, and there is an if block and else block. These are again a representative of what exactly happens. So imagine that you have a loop that runs for like, I don't know, thousands of times, and then your CPU starts seeing that you're taking the if block always, like most often times, right? So basically it starts looking at that, and then you're not taking else blocks. So it starts kind of doing a speculative execution that, okay, you are going to likely take this if block because I know that historically you have taken that thing, and let me basically help you with that one. With that, it actually optimizes a lot of the things in terms of the instruction caching, in terms of obviously there's no data caching, but instruction caching is done. So a lot of the I would say the boilerplate work that it has to do, it actually kind of caches that and ensures that you don't spend time on those things and then go to the result. But what if your condition that you thought that it was a speculative execution and it happens to be not true anymore? So it has to wind up all the like extra work that it has done ahead of time, and it has to wind up back, and then it has to flush your cache. It has to flush your the pipeline so that it kind of gets a reset, like a staged reset, and then it can go back into the else block here. Okay, so to demonstrate this, I have a very interesting example here.
Rewind.
Sorry.
Yeah, no, sorry. I think you just meant rewind. Like before committing, you can just go back, step back through the whole
Yes.
execution and just execute the
Yeah.
other block.
Yeah, it has to rewind that. It has to rewind. I mean,
Yeah.
like stack unrolling happens. A lot of the other like
Yes,
pipeline
yes.
flushes happens. Cache
Yes.
will be
Yes.
invalidated. A lot of that stuff
Sorry,
actually goes on.
sorry. Stack unrolling happens. That is stack is a compiler construct. No.
Oh, even it is there at the.
No. Yeah.
Do you mean execution stack or?
No. You're talking about the program stack.
Yeah.
We are talking about another stack that is like a hardware
PC, I
data
mean,
structure kind of a situation.
yeah. If you have heard about the program counters and how it
Yes.
actually goes, so basically that's nothing but a stack, and then I mean, in a simplified version. So
Okay.
Yeah.
I'll get back to that one.
Okay.
Yeah. We'll get back to that later.
Yeah. So like we saw how the branch prediction works, but what are the real impacts of these ones, right? So this is a simple example. So I have broken down it in three parts here. One is like very simplified uh, C++ code, which is like a vehicle as an like a base class, and it has a very simple method called max speed that the vehicle can attain. Okay, and yeah, since it's from there we are actually creating three derived classes: car, bicycle, and motorcycle. So each one of them have their maximum speed that they can attain. Okay, so this is just in case here, and this is where we are having one benchmark. So what we are going to create is we are going to create 5,000 entities of each one of these kind here. Okay, so close totally we have 20,000 vehicles in our vector that we are creating. And what we are going to do is like I'm going to calculate again, this is a hypothetical example. So I'm just kind of going to sum all of the maximum speed for all of these vehicles. Okay, and what you are going to do here is like you're actually navigating through this vector. And then in this vector, you're going to, let's just sum it up here. Now, what happens in this case is since we have added these vehicle types in a sequence, so you have like first 5,000 will always be vehicles. Next will be cars, there will be a bicycle, and then motorcycle. So it's kind of a sorted vector. So that's the reason it's a VF sorted. Sorted is the name for the benchmark. In the second case, we do the exact same thing, but what we do here is like we shuffle them in a randomized order. Okay, so that you can see that I have exact same 20,000 vehicles, but now I have shuffled them across across my vector. This remains the same thing. It's just calculating the total speed. And when I run this, okay, and the code, so what do you expect to see here? Like, I'll keep a little interactive here. So if you have anything that you want to share, you can open up your mic and then share. So does anyone have anything? Okay, I'll just run through the next one. So you can see that this is the branch prediction difference here. So this is my sorted list. So the lower is always the faster. And this is my unsorted or basically shuffled one. So you can see it is almost how many times? It's like 5 times slower that we saw. So this happens because of your branch prediction. Okay, because your branch prediction is assuming that next 5,000 vehicles are all, let's say, car or types, and then basically it kind of caches all those instructions so that it is there. But when it identifies that there is a wrong branch it is taking, it has to flush that, and that's basically the penalty that we are paying. So here is where you can see this. In this example, it is a 5 times penalty that we are paying. I'll skip this once. Again, although this is my favorite, but then how this
That's fine.
actually how this actually impacted the browsers, because let's say that we are kind of doing this, and because I mentioned about that you have to flush your caches, you have to kind of do a lot of unrolling of that thing. But what if between that state where your processor has those caches contains all that data that it has kind of added or like executed in terms of for doing the branch prediction or a speculative execution, before it could unroll that, what if you have access to that cache and try to read that up? Okay, so that's exactly what happened. It is still happening on your processors. Your processors and my processors are not patched yet. It can't be, because it's a hypothetical scenario that if you can run something which is faster than 4 gigahertz, that means between the cycles, you can steal the cycles and try to inject something and then try to read that. It's a fairly complex things to kind of produce, but not really difficult. okay, to recreate that. And that's where two of the very prominent things that were shown is the Spectre, and then there is another one. Again, I have just kind of linked them here and just kind of giving the idea that, okay, what can really happen. So these topics are very, very involved again, and then they also require a lot more understanding on the lower level systems. But if anybody is interested in kind of knowing this and then trying to understand, so you should read these details. I'll share. I mean, I have linked it here. So what really happens is in your browser, you are trying to execute a JavaScript, and then that JavaScript kind of creates an array in order to create a speculative execution scenario. And if your render process is kind of keeping something, or if your browser process has, let's say, your password manager has kind of access to you have tried to access that, might be there. It might be there might be a chance that these data will be available here, and the Spectre actually showed that you can actually read that. Uh, Now that a lot of the data is published, so that you can see a lot of the videos are there, like how people have shown that. So in fact, this was discovered in Google Project Zero. This is basically a kind of security arm inside Google, which actually looks at uh, security aspects of various products, and then they do a lot of the work there. So there's a there's a great talk if you are interested in knowing what really happens here at the like clock level frequency. You can read these two blogs, very 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 detailed blogs there. And okay, so we showed that, okay, this is possible, right? But then your question is like, how did we resolve this? So one thing is, as I said, it's unlikely that you can solve it at the hardware level. There is some like research that is ongoing. There are like a lot more literature how to mitigate that. It cannot be fully solved, but it can be kind of isolated in a way, or like detected in a way that it can be prevented. Okay, it's not a definitive. So I have like a few things that I would probably retweet after this thing, so that folks who are interested to read more about that can read that. Um, so for the browsers, we actually throttle the JavaScript execution when you are actually trying to create something like these shared buffer arrays. Also, those are like very high performance things. So that I mean, browsers are a little bit blessed that way, because we have to just tweak your JavaScript engine, and then like you are at mercy of like what browser engine is providing it to you. Okay, so we basically just tone down the execution time that we offer to these ones. So basically, we throttle the executions of these things, and those are not fully jittered, like to the kind of the maximum level that it can attain. And that's where how we solved it. Now, this is a very famous quote from Benjamin Franklin and Andreas Klink, who is like very interesting personality who is building a ladybird. And I happen to know him from the WebKit Times. I met him in person as well. So he tweeted this, but he gave me also a thing that, okay, from where it came. So Benjamin Franklin said that those who can give up essential liberty to obtain a little temporary safety deserve neither liberty or nor safety, which he tweaked it. Those who would give up essential security to purchase little temporary performance deserves neither security nor performance here. So, and then there is a basically a thing. It's a meltdown inspector. This instantly made me think of the meltdown and Spectre vulnerabilities. They gave up a little. That means we compromised on not executing your shared buffer arrays at like the maximum performance that we can attain, but we kind of toned it down to achieve that security. And that's the reason this is the history of this code. All right. So with that, I think I am concluding this talk. I know, I mean, I scratched a lot of the surface, and I really wanted to go inside deep for each one of these ones, but I'm always happy to kind of join back, or if you have any questions, please let me know. I'll be approachable on Twitter. And yeah, I think that's about it.
Awesome. Thank you so much, Vivek. This was really a lot of fun and a lot of good stuff. Really, really enjoyed it. Thank you so much. Also, people here who have not been looking at Vivek's Twitter posts and stuff, please go and look at them. He has been sharing so many good things. And it has been a pleasure going through some of them, right? So it's really good stuff. And I'm sure you all have a lot of questions. It would be good to ask them. If you can unmute and ask your question, like raise your hand, and we'll get to you. If you do not want to unmute, then you can ask in chat. But we'll be prioritizing people who want to interact with Vivek and ask questions that way. So, okay, just start raising your hands, whoever has questions, and feel free to ask your questions. Again, thank you so much, Vivek. Also, the other thing is I wanted to call out the team, the OTC team, because there has been a lot of work going on behind the scenes to get all of it working. We have Alpesh recording, we have Darshan, Advait, and everyone coordinating the session, making all the posters, the social media posts, and everything. There's a lot going on behind the scenes. So thank you so much to the entire team as well. They've been working quite a bit, right? Some are on jobs, some are in college with exams and everything. So thank you so much, everyone. Appreciate it. And yeah, let's start with the questions. On the queue, we have Nofil first. Go for it, Nofil.
Okay. Hello, am I audible?
Yes.
Yeah.
That was your question, right? Thanks. Okay, we can move on. No, sorry. Go for it.
Okay. So my question is simple. We see one common issue in using websites. The or snap, the website has crashed. So what's the most common issue that causes this kind of error?
So again, just to give a very short answer, there is not a single point of failure. There are like a number of things that can go wrong. One thing could be you have caused an out of memory thing. You probably your JavaScript is just accumulating too much of the memory, and browser might evict you for that one. There might be a case where you have developed an exception in the code, C++ code, and then as part of that one, it has to close. So like various different reasons can be there, not a single point of this thing, and each case is very unique. So for example, when you are using WebGL, so it goes into a different territory altogether. When you are using like Google Meet kind of apps or WebRTC, it has kind of a various different vectors. It can go wrong. So not a single thing.
Okay. Before we move to the next question, that should remind me, let's just take a picture. So whoever is comfortable in switching on your cameras, please switch on your cameras. If you're not comfortable, that's okay. But if you are comfortable in switching on the camera, we would encourage that, and we can take a screenshot. So yeah, just we'll wait for, I think, a few seconds. If you're comfortable, please switch on your cameras. Thank you to the people who are switching on their cameras. One second, let me just change my.
Will you give a timer, countdown?
Yeah, I will. 1 second. I am just trying to fit everyone in my screen. I'm trying to figure out where that setting is.
Harsh, that's fine. I'll take the screenshot. I have everyone on my screen.
Okay, you have everyone on the
Viranshi?
screen? Okay,
Yeah.
so we'll, yeah. Okay, let's take the picture. Pranav, give us a countdown.
Yeah, is anyone like, I think there are many people who haven't turned their cameras on. Do you guys want to turn on? Like, we'll wait for like 5-10 seconds if you can. It's good. If not, we'll just click.
Okay.
Yeah.
And Pranav, make sure you're in full screen.
Yeah, I'm in full screen.
Awesome. Okay, give us a countdown, and then yeah, let's wait for people yeah, let's keep the chat silent, please.
Yep, please. All right, I think I'll just go ahead. I'll give a count of 3. 1, 2, 3. Yep.
Thank you, Pranav.
Yep.
Did we saw a flash on Pranav's screen?
I think I also saw it. It was a good
प्रणव ऐसा
effect.
कैमरा लेके बैठा है. Yeah, I know.
नहीं, I am not, but okay, sure. Very interesting.
हाँ.
But yeah, all the raised hands went down apparently.
Yeah, okay, let's raise hands again for whoever wants to ask questions. On the queue, I have Ritik right now as the first person. So Ritik, please feel free to ask.
Yeah, I just wanted to. Hello, am I audible?
Yes, yes.
Yeah.
Yeah. So, Vivek, could you reiterate on the point that you discussed that on the rendering part, where you once you type world with a delayed input, so how it backtracked, like basically backtrack that part where the renderer part was taking a lot of time. I didn't get the backtracking logic at the hardware level on the app that you showed, which was, I think, I forgot that app.
All right. Yeah, I think I got what you're kind of asking here. So definitely there are two aspects that you look at it. One is if you are interested only in what is going on within that particular web app, so you should restrict yourself to being on the performance panel for the DevTools, and there you can actually see all the fragments of the traces that you are interested in. So that would give you what is really going on inside your web app. But if you want to kind of zoom out a little bit and then try to understand what is really happening across the different processes that I talked about, just like a browser engineer. So I would highly encourage you to do that because that's how you would really get what is going on there. So the backward traceability is one of the features that the Perfetto provides, where let's say that you have an input event, like when you type H, right? So actually it generates 3 to 5 different events. So this is not a single key press. There are like a key press, key down, key up, and then there are like few more things that actually happen. So there is a back and forth for each one of these events. So for let's say single key press, you'll have like 5 events that will be fired onto the renderer, and renderer has to acknowledge that it has processed it. If not, it has processed, it has to give back saying like, okay, I don't want to process it. You process it. So that there is a lot more things actually are happening. And if you want to know how these events are actually fired and how basically the renderer is kind of responding to that one. So you will get those backward traceability events inside the Perfetto trace. So for that, again, this is not a very short answer for your question. It's a very involved one, but the backward traceability comes from some of the features from the Perfetto and like how we use it inside the browser engines.
Understood. So mainly, if I want to check what is blocking, I can check the in the DevTools. I can check the what is the main thread, which is
Yeah,
why getting blocked. And if I really get deeper into the facts that how hardware level things are happening, then I can backtrace and then basically check what's going
yeah,
on.
yeah.
Yeah. Thanks, Vivek.
Awesome. Thank you. Feel free to ask follow-up questions, people, and feel free to jump in at any time. Alpesh, go for it.
Hey,
Sorry.
also
Yes.
before Alpesh go, uh, I think the screenshot was not very nice. Do we want to go again?
Um, sure.
Nah,
I mean,
no, I have taken them. I shared in the
Let's
group.
let's see.
Okay, thank
Okay,
you,
yeah,
thank
that's
you,
great.
thank you.
thank you, Ankush. Really
Yeah.
appreciate you. Also, next time, let's make this a thing. But okay, Alpesh, go for it. Sorry.
Yeah, since WebGL was mentioned, there are many sites which use WebGL for like DDoSing the user's device. Let's say like एक threat actor है, he just wanna like disrupt the user from using their entire device. So when a WebGL websites open up and it renders a few hard particle which uses GPU. It essentially breaks down the whole process and your whole device kind of starts hanging. So very particular browsers like Opera GX have some kind of mechanism which uh, gives basically a pop-up to close the tab. So how do general security engineers handle these kind of issues?
Right. So I will not answer it from the security engineer's perspective because like there are like various different things that goes on. I have some knowledge about it, but then I would refrain from actually saying what exactly happens. But I can give you how Opera actually implements all of that logic that you mentioned, as well as like how browser does the scheduling of such rogue apps. Uh, Not really rogue apps, but one thing, as I mentioned during the course of the talk, is about using the queue that if your web page is visible, only then the WebGL context would be created, and then only then you would have an access. But again, if we see that you are actually abusing a lot of the main process, I mean, because V8 is running on inside your web page, which is actually running your WebGL interactions with the JavaScript. So we would know at what sample that you are trying to access this, and we would also see if it is something doing malicious activity, which is kind of stalling the main thread on the renderer, as well as it is trying to do a lot more work on the GPU process. So there are like a keep alive messages that actually flow between the like various different processes here. And if you don't get to hear that, you can actually do certain very interesting things that I will show you. If you go to a URL right now, I'll probably quickly
You're not
share that.
presenting, by the way.
I'm sharing this back again.
Okay, take your time. Yeah, yeah.
Yeah, because this is very interesting. You might love to do that. So if you type these ones, right, from URLs, it will be small, but I'll just show you that here. So if you visit these ones, right, list of Chrome URLs. So this is the URL. I will paste this in the chat here. Okay, can you, once you have seen that one, so it has, these are the debug URLs. Okay, so you can actually call these things, which is like GPU crash, GPU hang, GPU this thing, renderer hang. So you can create a short hang, you can create a long hang, you can actually create a GPU clean, you can actually kill the GPUs, try to do all those things. So you will get a message saying like your page has gone non-responsive. Would you like to kind of close this? It will also, let's say some of the critical processes like utility process is killed, GPU process is killed. It actually goes ahead and respawns it back, because if I don't get to hear that, those are the critical infrastructure processes. So those will be respawned again. So in short, it has a lot more infrastructure in place to handle these like usual suspects. So DDoS, or like DOS basically, is a very prominent thing where you would use the primitives like WebGL. WebGL is the little old age, I mean, like old school thing now, because you should be using web GPUs. But then with the web GPUs, a lot more comes in terms of the security considerations, and a lot more care has been actually handled in the craft of those APIs. So if you happen to go and see the specs, you can actually go to W3, not W3 schools, but W3 things for each one of these specs. So you will have a dedicated section for the security. Okay, so it's the browser security is of the paramount importance for these specs. So I don't know, Alpesh, if I answered your question to the full extent, but this is the max that I could answer for the context.
Mm, my question is why you couldn't answer the whole thing? Like, is there a like the answer is long, or is there some other reasons?
The answer is long. I mean, because we have
Okay.
to move to the other one. I mean, I can go into the details of these ones, but
No,
yeah.
that's
All good.
fine. Yeah.
Yeah, you're all good. You can answer as to what, as like what detail you want to go into. That's fine. Mohit, Alpesh, by the way, your question is answered, right? You got the gist, right? Okay, great. Mohit, go for it.
So you mentioned that a browser affects an process if it has some sort of it illegally access some memory. So how does it know? Like ideally, the OS should be managing that. So how does the browser do that? Is there some sort of context?
No, that's a two-part question. I mean, two-part answer to that one. So OS will manage the process level memories, like how the process orchestration happens at the OS level. but the browsers, they actually manage their own memory. So we, let's say how you use the JavaScript inside your application or like the web app is decided within the memory management of the render process. And there is a partition alloc if you're familiar. If not, then you can also read about that one. So partition alloc is one of the memory management thing that Chromium uses, and that has been also prominently used in other things. So if one counter question, not really counter question, I just want to know when you say that it's a illegal memory access. So can you just elaborate on that? What's exactly you're trying to portray there? Because see, when there is a illegal memory in access, it will be flagged at the processor level, because your processor is also capable of finding that you have the base memory pointer. I mean, in at the hardware, and then every address you are trying to access, if it falls not within the range that is allocated for your process, it would be flagged at the uh, system. I mean, like hardware level, it will be kind of giving you a signal, or like we used to call it as NMI, non-maskable interrupt. It will basically come back, and then you, as part of that one, you would handle your exception routines. But again, before going into the details, I want to know from where you are trying to, because if you're talking about the JavaScript, I can assure you like how these things are handled inside the V8, but just want to know the scope of the question. I don't know who was asking the question, but if
So
you can help.
sorry, I didn't realize my mic was mute. So I said that in a more general sense, it does not need to be within the process. It could be anywhere in the system.
Yeah, so then this is basically handled at two levels. One is at the hardware level, one is at the OS level.
Okay, so how does the UI process know as to where exactly has this fault occurred? Is there a context manager similar to Android, or is it something different?
No, I won't know much on the Android's context. I mean, this one, but then you would have these trap handlers that you are setting up in your code. That if there is a certain signal is raised by the OS, you would want to handle that. So you have these trap handlers, signal or like signal handlers more to understand from the system side.
Okay, so the trap, I believe the trap flag would be raised for for a specific process, and then the browser would manage it accordingly as a parent process.
Correct.
Okay, that's cool. And apart from that, could you speak more about the security model aspects in a more general or brief sense? Like how does the main UI process sandbox every render process? Is it something similar to Docker where it uses namespace, or
Okay, so each OS that where the browser runs, right? So it provides the primitives of like how the sandboxing is implemented. So the sandboxing that is used on Mac uses something called as I forgot the name, but I think it was something called Handbrake or something. Not really Handbrake, but there is something which actually is provided by the macOS. I think SSE comp is what Linux provides, and Windows has its own sandboxing primitives. Where what is the sandboxing is, let's say when you are trying to read a file, right? So at the bare C level, you will have fread or fwrites and fopen. So when you're trying to make those system calls, and if your sandboxing is in place and doesn't grant you that access, those system calls will fail for that particular process, because that will be actually implemented at the OS level. And we actually make use of that one and then build our own custom policies. So render process will not have access to the file system. It will not have access to like networking, like network calls are also used using, let's say, system calls. So you will kind of, those will fail.
okay,
And
so it's more like we're kind of more at the mercy of the OS for the security implementation.
yes.
Okay,
And
so
if if you are really interested how this was done, you can read about the native client, which Chromium actually implemented, which actually has evolved into WASM, like WebAssembly. That's another very interesting topic of, I'm very interested in that. But it involves modifying your compilers to remove that. So these are the compilers which are actually just-in-time compilers, which are actually part of your Chromium or like basically your browser, and those will remove those calls on the fly. Okay, so that way this is actually handled at that level.
Okay, and I had another question regarding vsync. So, is the vsync thing only for the rendering part, or is it like, so I wanted to know, is vsync for the works for the processing part as well, or is it just the rendering part?
So
And
we think is more of a graphic event from your GPU or maybe the hardware underlying. It is not relevant to, let's say, I mean, it is not only restricted to your render process also. I mean, we use that from the hardware as a clock signal. It's like a consider like a clock. It's a ticking clock, which is like a related to your graphics output.
so is it
So
something like basically every process kind of manages its buffer at some point when it's dirty, the vsync clock
yes,
repaints the entire thing?
you'll have to you have to get your frame and then frame buffer. You have to actually flush it under the GPU. I mean, if you are using OpenGL, you have to flush it. If I just simplify it that way.
Oh, okay, got it. Thank you so much for your time and everything.
Yeah, thank you, Mike.
Okay, before Rishit's question, we have a question in chat. I'm just going to send it again. Ayush Shukla asked this question. What would happen if a browser switched from a multi-process model to a true microservice model, where each component is isolated and communicates via lightweight RPC calls? Would the benefits of modularity and fault isolation outweigh the overhead of serialization or an IPC, or would the performance cost be too high?
That's a great question. One thing is, as I said during the course of the talk, is the browser has become a commodity, right? So
Mhm.
let's say when it's a commodity, you expect it to be fast. You really don't want to be waiting. So think about it. If you're taking like few milliseconds extra, you would literally feel that difference. So
Yeah.
even if I can have an like a overly not simplified or overly complex architecture in terms of how I can kind of create this microservices architecture, one thing that we will have to understand that every such architecture comes with its penalty. So let's say now it's a trade-off between whether you are okay kind of removing certain level of performance gains by doing a continuous RPC calls for doing a lot of these microservices architecture. And then at the end of the day, you have to kind of outweigh these like penalties that would be incurring due to the architecture choices here. So browsers, as I said, as a commodity, product, you have to have a reliable thing and it has to be really fast. So right now I'm connected to my I'll just give you a gist of the things here. Okay. So right now my laptop is M4 Max, which is like 120 hertz display if it is connected to like on its internal display. But if it is connected to a monitor, it is running at 60 hertz. 60 FPS. But when I'm running this at on my local machine, I mean, on a native display, it runs at 120. So basically, you just get 8 milliseconds. So the train track that you saw, it gets half. So in 8 milliseconds, you have to do a lot. So every addition of, let's say, IPC costs us like these milliseconds. So it all depends on what is the trade-off it is lying. And think about it. Can I run like high performance gaming using Wasm? Okay, it's not only about the traditional website that we have to render. Those won't need that kind of heavy lifting that is needed in terms of running them at 120 hertz. But what it really requires is that we can run them at 120, but also the games that would run. If I can run the goals for the browser is like to be the runtime where various different applications can be running together, and then yeah, I think these are some of the points. I know this will not answer everything in one go, but it has its own pros and cons, and it chooses performance, and that is also the reason that Chromium is kind of notoriously known in the tech circles for hogging resources. It's for these reasons.
Okay, so we have one question in chat, and then I have one question. If there are any other questions, let me know. But I think for now, these are the two questions. Okay, so the question in chat from Mohit is, he has a question regarding Perfecto. Perfecto. How are we so sure that the delay is always because of the function call? Do we take multiple readings like a physics experiment?
Like it could be through multiple sources. It could probably be because of another process which is consuming a lot of. So do we
Okay,
count the
so
number of cycles or is it something else?
samples, basically samples. And when you have actually instrumented a particular function, so you would add the probe at the beginning and the end of it. So think about it like a RAI, research acquisition is initialization, uh, like a like a design pattern. So when your function goes out of the scope, basically unwinding of that trace event happens, and then basically that is where we actually calculate the start and end. So as such, you really don't need multiple readings because these are the kind of factual details those are presented in the perfecto. These are not basically approximations. Okay, so at the time of entering of your function, a timer would be recorded and the end of it will be recorded. So if you see a longer segment in your trace, you would know that okay, it is indeed because there is something going on there. I wouldn't say still wrong because that is the finding that you will have to dig into because you might be still needing that 1 second for doing like bazillion things that you would want to do. But yeah,
Like as in there could be multiple processes running on the system, so the delay could be caused from anywhere. So is it like we count the number of cycles to be or something like that? Or and also another question, does every process have its own JavaScript engine, or is it some sort of
no,
IPC that has been implemented?
each renderer has its own instance of the V8 engine in case
But
of Chromium-based.
doesn't that make it too heavy? Like,
So that is the price. I mean, because see, you if I don't do that, how will you do the state management? Because JavaScript is it's not really a stateless thing that you're doing because you have a state, you have a context of like where exactly it is happening. I'm getting an echo.
Yeah, Mohit, the reason I was muting you before was Mohit.
yeah, yeah, I'm there.
Yeah, the reason I was muting you before was because there's an echo when Vivek is speaking. So can you please mute when Vivek is speaking?
Oh, okay, sure. I'll just mute myself.
Yeah. So on the V8 front, right? So a lot of the context is there, and it has to be per thing. And if we were kind of doing that, so actually the cost of managing a V8 instance as a kind of a microservice in a separate thing would actually blow it up because you would want to create those many instances in a separate process. Plus, there is a cost of an IPC. So when we are talking about, I mean, in another talk, I talked about how how browsers juggle the JavaScript. That would have actually given you the insights like why browsers would need that each instance running locally there.
Okay, so it's mostly because of both security and performance reasons.
Yes, security and performance.
Okay, got it. Thank you so much.
All right.
Okay, I think it's getting pretty late for
I'll
Vivek.
probably take one, probably last question if that's okay because
Okay.
yeah, I have to go back home also. So
Yeah, that's what exactly. It's getting pretty late. So, Ritik.
Yeah, it's just a follow-up question to Mohit. Like,
प्रणव का ले ले यार सॉरी यार प्रणव का ले ले बेचारा 3 बार
It's
लोड
fine.
हो
It's
चुका है
fine. It's fine. Let Ritik
okay,
go. It's fine.
I'll probably I'll wait for the last question from Pranav. Okay,
हाँ, yeah
Thank you.
you'll just have to open up your
Okay.
video though because it I'm just kidding. Sorry. Yeah, go ahead, Ritik. Go ahead.
yeah, sorry. It was just a follow-up question from Mohit. Like, I didn't get that part where you said each renderer should have their own V8. So, as in each application can have multiple renderer, right? As in, um, like
Okay, I'll
instance of
think.
renderer running.
so I guess
V8.
the point Sorry, Vivek, just so I guess it
Yeah.
is mostly about uh, your renderer also runs JavaScript, so that's why it should like isolation running of JavaScript. That's why. Am I right or am I
Yeah,
wrong?
exactly.
Yeah.
So your JavaScript also has access, as I was talking about, there's a V8 to C++ bindings, like JavaScript to C++. So there's a lot more state that is actually there. So your DOM is actually driven from your JavaScript. So not driven, basically it has access to your DOM as well. So then there is a concept of web workers, if you have used that. So a lot of these things are actually, can you see my screen? I have started sharing this back screen.
Yeah, visible, visible.
Yeah, yeah.
Uh, Okay. So I'm just going to briefly go through this because
Sure.
it's a
Up to you.
very, very interesting thing. But okay, so this is the high level what really happens inside the JavaScript. Okay. There's a parser, then there's a AST that is created. From this AST is what is run by the engine, and then this is the interpretation mode. Then there is a benchmarking mode, like basically how many nodes are actually visited by the interpreter and like if this is repeating, so it would actually create I mean, it would move that into a JIT. If not, then interpreter is actually using the bytecode and then it would run. It would be running a little slower space. But the other things which are I just wanted to highlight here is yeah, I see when you are creating this const a equal to 100, which is running inside your JavaScript, I mean inside the web page, right? So this a or these values are should not be accessible to anything else. So this is like part of your renderer itself. Okay. So this is where I call it as a state. So you can have two web pages and then the exactly same website that you're loading, let's say google.com. It has this value a equal to, I mean, this, let's not assume that this is a const. This is like, let's say this is a var a equal to 100. Somewhere down the line, you are modifying that a equal to 200, but that would happen only in first tab of Google. So let's say if you have happen to open the same Google page on another tab, that value will still be 100 there. So this is the state that we are talking about. And also a lot of your DOM interactions go through, you might have, I'm pretty much sure that you would have used document query selectors and all those things. So that's where you have access to your DOM. So those are part of the JavaScript execution. So for these reasons, it actually puts everything inside a single instance, not single instance. Each instance of the web page or the tab has a V8 engine.
Vivek, uh, you said that no cross like tab process access, right? So
Yeah.
basically isolation of JavaScript
Yes.
variables and data. But what about DevTools? DevTools, I guess, is a different process. So it has special privileges or it runs on the same renderer?
No, that's a great question. The DevTools that you see is actually written in JavaScript, but it runs with the privileges and it has access to all the bindings which are private bindings. So through which it can access all the it's a backdoor. Think about it like in a very simple terms that DevTools provides you the backdoor into the web page. But yeah, it is like very
Okay, so
very much
it,
controlled.
it basically has some special access, kind of special privileges to.
Yes. So I am just going to show you
Yeah,
what
I
we
have
have.
seen DevTools for DevTools.
Yeah, DevTools protocol.
Wait,
Okay.
what?
Yeah, you can open DevTools inside DevTools as well.
Oh yeah, you can do that. It's a
You
inception
can
there.
Inception है
open
भाई DevTools का वो.
you can open DevTools on extension contexts.
No, you can open that one as well.
I know.
Yeah.
I posted this in OTC a while ago.
Yeah. Okay. I don't know who was asking the question because I was not looking at the screen, but
Darshan.
Darshan.
this is the Chrome DevTools protocol, which has access to all of your internals here. So uh, the one that you asked, right? So it has the WebSocket. Actually, it uses a WebSocket to actually relay this information back and forth. So your DevTools communicates with the rest of the tabs using WebSockets. That WebSocket is opened inside the browser process, and from there the orchestration actually happens. So you have access to everything here.
So essentially, DevTools can access, like if I open a DevTool in the Meet, it can
Yeah.
also like theoretically access data inside another tab.
Yeah, I mean DevTools
Okay.
is part of the browser. So yeah.
Okay. Got it.
Yeah. Pranav.
Do you, if it's fine if you want to leave, I understand it's very
Mhm.
late. Like
It's
I'm just trying to
okay.
like encapsulate and summarize whatever he has talked about right now. And
Okay.
I think Mohit also asked one question about like V8 making multiple copies of itself while like different tabs are getting spawned so that they can render. I don't understand why that is going to be a problem, because from my perspective, even as an interpreter, you will have like different sections, segments of your code, and it's mostly going to be like a copy on write sort of a protocol, where each process, when it tries to just spawns a new iteration of that, you can just have like same pages that are linked to the page table of that new process, but the stack or the heap or the other sections that are going to be dynamic, you can just swap that. So I don't understand
Cost.
why that is going to be a very big
No,
power.
it's not a concern that we cannot do that. It's just about the timing and
Hmm.
the cost of the co-locability. I mean, let's say when it is part of the same process, you have a lot more control, lot more faster access. So the swapping
Hmm.
cost, the context switching cost, in
Hmm.
a nutshell, is like way too high. And imagine that, would you love to have something like you have moved your mouse and then your page is not responding enough
Yeah. Hmm.
fast because your browser is
Yeah.
doing some kind of very interesting architecture experiment. So that one.
Got it. Yeah, and in terms of like in general, when you talked about like the Spectre meltdown problem, is that like dynamically, do you just reduce the speed of the JIT compiler so that
Yes.
like that, so that happens dynamically?
There are two parts to it. One is like the shared buffer arrays that I talked about. Those are like very
Hmm.
high performance arrays that you can create in JavaScript. Those are actually introduced in order for you to kind of do much more, provide you to the native experience so that you can do faster
Hmm.
executions. So with that intention, those were added to the JavaScript spec. But with the advent of, let's say, Spectre and
Got it.
Meltdown, they are actually throttled in for everyone. Okay, those are
Got
not
it.
dynamic decisions, but dynamic decisions are some of the ones where whether I should do a jet or I should do an interpretation, right? So that's where also a lot of these decisions are made. So
Got it.
you can read about this vulnerabilities called V8 type confusions after every once a vulnerability has been fixed, right? So I think there is a MITRE Mitre website where you can actually see how
Hmm.
many of the Chrome related vulnerabilities are coming from V8. And if you search for V8 type confusion, so those are some of the things where the the security team identifies that, okay, there is an issue due to
Hmm.
this execution sequence of V8, and because of which we are resulting into a type
Got it.
confusion. So if you guys are familiar with, let's say, an opaque types, right? So you can have anything that you can dump into it, and then you have basically an identifier to denote whether it's an integer, whether it's a floating point number, and all that stuff. So think about like a
Void
struct.
pointer or something.
It's a struct void pointer, and then there is an enum
Hmm.
denoting what it is. And imagine that you are overwriting that let's say the type identifier with something else. So your JavaScript V8 is going to
Typecasting.
interpret, yeah, it is going to typecasting. It all boils down to the
Hmm.
typecasting. If it, you can kind of trick V8 to think that, okay, it's a right typecasting, and then eventually it identifies that it's a wrong thing. So some of those things have resulted in doing some sort of dynamic clamping, I would say. But
Hmm.
again, it's a reactive. So certain things are known. Okay, this is the problem during the,
Got
because a
it.
lot of the compiler engineers work and then they bring in the experience from the rest of the world, right? So they can actually incorporate
Hmm.
that. But then
Yeah.
with the kind of ever increasing field of security, and the browsers are exposing, it's like you are going in open on the street and saying like, okay, these are my credit card details, these are my these things, because browser is so much
Yeah.
open there. Okay, so and then it is we don't like the renderers. Basically, when I say browser engineers, we don't really like the renderers. That is because we inherently treat that's the security hole that I'm kind of allowing you to run on my machine. Okay, so
Got it. Yeah.
that
Mhm.
we come from that kind of thinking again, just to keep it casual, but
Yeah.
yeah.
Okay.
Got it.
Fair enough.
Yeah. Also,
Okay, Pranav.
do
Yeah.
you enjoy
Okay.
do you enjoy architecture more or the like software side more?
Which architecture? Because I have like now
The
started,
hardware.
yeah, hardware. I mean, like top of the stack, like full stack. I'm a full stack developer, so so from
Yeah.
Yeah.
hardware to this one.
In
I
the
mean,
true sense.
I
In the true
enjoy it
sense, yeah.
from these ones. So uh, I mean, when I started seeing how different processor families are kind of doing these at the different level,
Mm-hmm.
it was so fascinating. It's so fascinating. And
It
one
is.
thing is off late I have developed interest is to do more of a teaching thing. I mean, to be really frank, because I have worked for now close to 22 years, and then now I feel that somehow uh, talking to a new kids is what I call them, because my kids are almost at the same age, like 14 years. So when I see that, the enthusiasm to understand that, okay, this is what really happens. So that's like a eureka moment. Not really eureka, but when you really understand that this is, oh wow, this is how it really happens. So once you have that
Aha
kind
moment.
of
When the
that
dots connect.
when the dots connect, exactly. So when you see that, okay, this is how it really happens, and then you have that, okay, wow, this is a great thing. So this is something that I have learned over the years, and now I would want to kind of spend more time. And that was one of the reason why I thought like this would be a good opportunity to connect with you all. Uh,
Yeah. Well, there were 50, 53, 54 people there. So, Vivek, I think you got to a lot of people.
Yeah.
But yeah, thanks for saying yes, by the way. And thanks for all the time that you gave us. We appreciate it. Thank you so much. And yeah, just thank you. This was just absolutely brilliant. I also have a ton of questions, but I'll save them for the future. But thank you so very much. We really genuinely appreciate the time you gave us. And thank you to the entire OTC team as well for working really hard to put this together as well. Thank you,
yeah.
Vivek.
Thank you so much.
Appreciate
Thanks
it.
everyone. Have a lovely rest of the weekend, and sorry for eating you into your like subsequent meetup.
Oh,
So
no. Thank you for your time.
all right.
Thank you.
Yeah. Bye everyone.
Take care, Vivek. Thank
Bye
you.
bye. Take care.
Bye. Good night. Good days.
Good night.
Thank you.
Same to you.
Bye.
Alpesh,
People who want to stay for catch up can stay.
yes.
Got it.
Alpesh, you can start.